Hello, my name is Nat, and today we are now going to do question 3 of 2016. Show that if f of x is x minus alpha squared for all x, then the function f is bilateral. Let us write down f of x. How do we show that a function satisfies a certain property through a substitution? We do the same substitution to the function, in this case 2 alpha minus x. We substituted 2 alpha minus x, and then we are now going to simplify. And here's an algebra hack. In the brackets, when the two terms are substituted by a minus sign, you can just as easily swap the two terms. This will make it easier, and in fact I will not derive it in front of you. The general formula is alpha minus beta squared equals to beta minus alpha squared. So x minus alpha squared is f of x. There, we have shown that f is bilateral. Therefore, if f of x equals to x minus alpha, then f2 alpha minus x, performing the same substitution, is 2 alpha minus x minus alpha equals to alpha minus x, which is not at all equal to x minus alpha. Show that if n is a non-aggregating integer and a and b are any real numbers, then this. So we can do this the long way or the short way. The long way involves integration, but the short way involves some visual thinking. Actually, the short way is faster and is more approved by the MAT. Here we go. So if x to the power of n, so let's draw it like this, is between a and b, then we are now going to draw this negative xn. This is a and this is b. Since the negative of a sine integral is basically just a swapping, so the negative swapping of a definite integral is the exact same as without a negative and without a swapping, which brings us to 4. Since f is a polynomial, a and b are any reals, well, we can apply this. Since f of x equals to axn plus bxn minus 1 plus d, I guess, then f of x dx is minus f of x dx. I'm so sorry, my brush wasn't working here. So suppose that f is any bilateral function. This is actually very easy to prove if we use some graphs. Let's assume our bilateral function looks like this, where it can look like something else altogether. This is alpha, this is t, this is 2 alpha minus t. We are now going to draw, this is a, and this is also a due to a reflection around alpha. So if f is a function, then we write g for this function. Suppose now that f is any bilateral polynomial. So g of t equals to t a alpha f of x dx, and then we do the negative swapping of the right hand side, which is the same thing if we do the negative of the substitution to alpha minus t. See, there, we have now proved it. Suppose f is a bilateral polynomial such that g is also bilateral. Well, there's only one function it can satisfy this. Well, before we go too much into it, g, keep in mind, should actually look like this. Something like that. And this is alpha. And this is 2 alpha. So sorry about my back to scale drawings. And since you can rotate the graph around alpha and it will still be the same, it will still be the same. So show that gx is 0 for all x. So what function satisfies this rotation property and the bilateral property? That's right, x equals to 0. Why? Because if we do a horizontal line around here, we rotate it around alpha, it will still be the same, and if we flip it around alpha, it will still be the same. There. See you in another MAT video.